Hello students, in this video we will study some of the applications of the electromagnetic induction. So the first application is the alternator, or what we can call the dynamo. The alternator is one of the principal sources of electric power, and it uses electromagnetic induction to convert mechanical energy to electric energy. Okay, so the alternator is a device that is used to convert mechanical energy to electrical energy by using the phenomena of electromagnetic induction. And the alternator, it consists of two main parts. The first part is the rotating part. The part that rotates we call the rotor, and this is the rotor here. It's this coil system. This coil is made up of N turns and it has a cross section S, okay? And the other part is called the static part, and we call it the stator. The static part is actually these two magnets here, okay? Again, we have the alternator. It is a device that we use to convert mechanical energy to electrical energy, and it's made up of two main components, the rotor and the stator. The rotor is the coil that rotates about a fixed axis, and the stator is the two magnets here, okay? We have a north pole here and a south pole here. It's actually a full magnet, so this is here a north and a south, and here we have a south and a north, but we want this side and this side. So exactly what we have is, we have this coil here made up from N turns, and it has another time the cross section S, and it's placed inside a magnetic field B. This magnetic field B starts from N and it ends at S, so it's a vector issued from N to S, okay? So if we want to go zoom in, here the orange arrow is the magnetic field B, and the yellow arrow here is the normal of the coil. It's the normal to the cross section S of the coil. And this coil here, it rotates with an angular frequency omega. So it rotates with an angular frequency omega. This omega is supposedly constant, and as it rotates, the angle between B and N, the angle theta, changes with the rotation. So what we say is that, let me just, okay, here. So the angle theta between B and N, so the angle theta is actually the angle between B and N, the magnetic field and the normal, it's time variable because it depends on the rotation. We can say that's omega t plus theta 0, where omega is the angular frequency. Let me just fix the angular frequency, t is the time, and theta 0 is the initial angle, or the angle at time equal to time t equal to 0. It's the initial angle, okay? So again, it's very like common sense, because the angle theta here, it's dependent on the angular frequency omega, so it would be omega t plus theta 0. If omega t is the angular frequency or the angular velocity, if you multiply it by the time t, you'll end up with an angle, and you add up another angle, so we have this angle theta. And if the angle theta is changing, we know that the flux, the magnetic flux crossing this coil at any instant t would be also changing, or it would be in terms of time, as a function of time. Let's write now the flux B, the flux of B. So the magnetic flux phi, we know that in the case of having a coil of n turns, it is n B dot S cosine theta. So it will be n B S, and cosine, what's the angle theta? We just knew that angle theta is omega t plus theta 0. Okay, so we have the flux phi is n B S cosine omega t plus phi 0. Let us put that in a rectangle just to emphasize it. This is the magnetic flux, right? And we have n is the number of turns, B is the magnetic induction or the magnetic field, S is the area of this coil, the cross section here, and omega is the angular frequency or angular velocity, and theta 0 is the initial phase or the initial angle of, like, let's say if this coil was initially not aligned with the magnetic field B, like it was not, the n was not along B at time t equal to 0, then we would have a theta 0. Okay, a theta 0 at time t equal to 0. That's it. Now, if you think about it, we have this magnetic field B and we have n. The angle is changing, or it's variable with respect to time, or it's variable, it's as function of time, I'm sorry. It's variable and it's as function of time. So theta is varying. It means that the flux phi, it's variable, and the flux phi is in terms of t. It's as function of time. Thus, we know that the electromagnetic induction, the variation of this flux phi produces an electromotive force E. And according to Faraday's law, we know that E equals to minus d phi over dt, right? So what we want to do now is we will derive phi with respect to time. Let's do it now. So minus d over dt of nbs cosine omega t plus theta 0. Okay, n, b, and s are all constants, so they are outside. Don't forget the minus sign here. Now, what's the derivative of cosine? It's minus sign. So we have minus sign and minus from the outside, that's plus, so we will end up with just sign. But we have something inside the cosine, so we need to derive those first. The derivative of omega t plus phi 0 is only omega, so it's nbs omega sine omega t plus phi 0. Okay, now we got the electromotive force E. So in this case, the variation of the flux produced an electromotive force E. Now, what happens is that I want you to pay attention to the form of this the electromotive force. So remember, the electromotive force is in volts, so we're technically looking at the potential difference. And this potential difference is of the form something constant multiplied by sine. So what we actually have here is that this alternator or this dynamo, it produces an alternating sinusoidal potential difference. Okay, so this device here is a device that produces electric energy, or it's a source of electric power, and the form of potential difference that it generates is an alternating sinusoidal. That's pretty useful for us. And now you'll say, but okay, there's an electromotive force, but how is the current transmitted if we don't have a closed circuit? What happens is that we have these slip rings here, and the coil is connected through wires to these slip rings, and these slip rings are they are the way that the electric current is transmitted to an external circuit. So these slip rings are connected to an external circuit, and this external circuit is supplied with electric current by this dynamo here. Okay, so now I think we got like an idea about how the principle of the alternator, how does it work. We're going to do a small recap. Again, we have a coil. So we have a coil of N turns. It's placed in a magnetic field that's oriented from N to S, from the north to the south. This coil is rotating with an angular frequency omega. As it rotates, the angle theta changes. So we have theta is as function of time. So it's omega t plus theta 0. This change in the angle means that we have a change in the flux, because we know that the flux is N, which is the number of turns, B as cosine theta. We end up with NB as cosine omega 0 t plus theta 0. It is a flux that's dependent on time as function of time, and we know that according to Faraday's law, here's Faraday's law, that the electromotive force equal to minus d phi over dt. We derive the expression of the flux. The derivative of cosine is minus sine, so this is minus sine, and we have minus from here, minus from here. That's plus, the constants stay the same, NBS, and the derivative of cosine u is u prime minus u prime sine u, and u prime is simply omega, so NBS omega sine omega t plus theta 0. And this electromotive force generates an electric current when there's a closed circuit, and this closed circuit is manifested by these two wires that are connected to these slip rings. These slip rings are connected then to an external circuit, and we have an external circuit supplied with an alternating sinusoidal current from this alternator. Yeah, so this E, it has the form sine. It's constant multiplied by sine omega t plus phi. That's sinusoidal potential difference. It will give us a sinusoidal current. Now, just to make things like more clear, we have this small application here. I want you to try to solve this application by yourselves, and I will be sending you the PDF on Teams. So please try to solve it till tomorrow. Okay? Thank you so much and have a great day.